So, growing up, I was the kind of kid who would come up with wild schemes to try to achieve my greatest dreams. Take, for example, my fascination with sports. As you said, I'm from Pittsburgh, and so naturally, I was a huge sports fan. And being so enamored with the games, I wanted to meet the city's star athletes. But I was a realistic kid, too. I knew I never really had a shot at being a player. I mean, just look at me, not looking a ton like the picture on the left. So I came up with another scheme. I could meet my heroes by being an umpire. That picture on the right looks a little bit easier to do. The only problem with this genius plot was that apart from knowing the rules, the umpire has to be good at spotting the ball, which, if you've ever been to a baseball game, you'll know is quite difficult. The ball is tiny, and it could be anywhere in a big wide field. It's like searching for a needle in a haystack. And if you find it, well, that'll make you the Hay King. And this skill that I had to learn as a child of finding a needle in the haystack is not so different from searching for a hurricane, a sandstorm, a polar vortex on the wide expanses of planet Earth. We're searching through 200 million square miles of surface area per day. And how many years of data do we have? Just 20 so far. So my aim is to allow you beautiful people to find whatever needle you're looking for, no matter how big or small it is. And to that end, I developed a multi-resolution search ranking pipeline. Let's first look at how normal image-based retrieval works. You've been beaten over the head on this, but AI is all about representing the input, like an image, as a small representation called an embedding, like 2000 floating point numbers. And there's one special property that these embeddings will try to follow. The similar ones appear closer together, and the dissimilar ones appear much further apart. So, based on that, finding similar images should be really simple. You just take images, pass them through a convolutional neural network, which gives you embeddings, and then you simply find other images whose embeddings are near to the query images. It is simple, right? Hold on. The last time I checked, the MODIS data that Worldview runs on gives back 1200 by 1200 kilometer tiles. But most AI models compress input to a size of 224 by 224 pixels, which means that a lot of details will get smushed away, especially smaller ones. And we don't want that, since importantly, some objects are tiny and some are huge, especially in the reference frame of an image, as you can see here. So given an image, having the ability to search at multiple zoom levels becomes important. As the ImageNet 2014 paper analyzed, bigger objects get better recognition. Pretty much anyone can search for big things. Searching for small objects, on the other hand, is hard. And not every phenomenon is the size of a Category 5 hurricane. So that's one problem to solve, searching for both big and small. The next problem in remote sensing is that a lot can happen in a 1200 by 1200 kilometer plot. There can be multiple phenomena in the same image. Heck, we're in 2020 when there were 5 tropical storms in the Atlantic Ocean at the same time. So if we're searching for 5 tropical storms, we want to get an image with 5 tropical storms back. But okay, we've complained about these problems for long enough. Let's skip the sob story and try to pick a concrete problem and solve it step by step. Here's a high resolution image. There's a lot of details in here. A nice green forest, hills, and yeah, a patch of fire. Say you're interested in finding other images of forest fires. Here's one approach. Divide the image into tiles, and you can make these tiles both big and small. And just so you don't miss anything, you can make them overlapping too. Now, we can build a search engine ranking pipeline to understand these individual tiles and aggregate their signal to ultimately determine what the user is interested in. This is similar to how Google and Bing take you from billions of web pages on the internet to the top 10 results you see, like if, for whatever reason, you wanted to know how to become an umpire. So, to that end, we can create a pipeline which gradually narrows down what we're looking for from millions of files to just 10. Each component gradually narrows down, or from top to bottom, it takes a longer time, and it scrutinizes each image a little bit more. But it has to work overall on a reduced number of images, so this is okay. This is like how any pipeline works, really. Even the internship pipeline. You start with a big old stack of resumes. You might see mine, which says I'm a first-year college student, and throw it out immediately, but presumably you do accept some. Then you give them a coding interview, and those who pass get an in-person interview, and you gradually narrow down the batch, paying more and more attention as you go along. But now let's look at each of the levels in our ranking pipeline. We'll start with level 1, where we cast the broadest net. I'll use this image for example. We can tile it very simply into 4 regions and find 100 nearest neighbors for each tile. Those neighbors will then comprise a candidate list. We'll move on then to level 2, where we might notice that many of the level 1 matches will be near the same location. What level 2 will do is group these similar images together and join them so that we can reduce the candidate set further. Next, we can move on to level 3, where we take this list of candidates and rank them using one of several mathematical strategies. There are several ways to go about this, and this is really the part that requires the most creativity and a little bit of intuition. To make it more concrete, let's say we have an image that has several matched tiles as various distances that you can see here. How do we translate this into a score that we can use to rank images directly? A simple strategy could be giving each matched tile the same vote in which image is best. But that lacks nuance and doesn't reward stronger matches. And just like our political system, we're not really interested in giving everyone an equal vote. If a matched tile is closer, it should have more of a say. So let's gerrymander things a little in favor of these closer tiles. One strategy that would do this is summing up the inverses of the distances between the embeddings of matched tiles. This rewards the really close matches with higher scores, but it doesn't put the distances in context to the other ones which have been matched, and it might over-reward tiles which are marginally closer than others, especially at low distances. The strategy that we ended up going for was a bucket vote. It first found a sorted list of all the distances at a resolution, as you can see at the bottom. It then gave each tile a score inverse to the percentile in which its distance lay. It took some of the intuition from the inverse distances strategy by creating an inverse relationship between distance and score, but by using percentiles, it added some context so that the strength of match is measured relative to the strength of the field. And now we would move on to the final part of the pipeline, where we've narrowed it down, we found our nearest matches, and this is great, because now we can actually get some data to see if all this nonsense really works. So in testing my pipeline, I went straight for the big guns. I chose the Microsoft Cocoa dataset, 34 gigabytes of data, 80,000 images, 80 distinct categories with 3 to 7 types of objects normally in the same image. But why Cocoa specifically? What are the advantages? First, we wanted something large enough to prove scalability. Second, it tests nicely for the 2 problems that we said that we needed to solve earlier. And third, small data sets are so high school. I'm in college now. Let's move on to something bigger. And also more concretely, we can reuse the ResNet architecture, which is trained already upon things like Cocoa. So it's going to be quite easy to use simply the ResNet 50 model. Here are some example images from Cocoa. You can see that there are a lot of objects in them of different sizes. A lot is going on. We need to recognize multiple images. So it's really perfect for our use case. Now to actually showcase some results. I tested my multi-resolutional strategy with square tiles with length 128, 256, and 512 pixels versus a traditional strategy that just searched for embeddings on the whole image. I graphed the F1 score, which is an industry standard, the harmonic mean between precision and recall, and I graphed it at the rate k, seeing how well the first best match, the second best match, the third best match, etc. of each model performed. First, you can see the differences, and the text finally makes sense now, on ranks 2 through 50, with multi-resolutional search in blue and traditional search in orange. We see a pretty consistent and sizable gap of 5 to 10%. Additionally, we see that multi-resolutional search has far less of a performance drop as we get to the later ranks, which is also desirable. But now you can check out what happens at rank 1. Multi-resolutional search jumps to 98%, while traditional search stays at around 50. Why? It's hard to say, but multi-resolutional search in practice is shown to be much better at finding not only the original image that was embedded, but also really, really similar ones. This might be attributable to approximations, which are used throughout, whether that's through approximate nearest neighbors or through things like PCA, which result in errors, but on aggregate, errors like this tend to go away. Regardless, we do see a marked difference on all of the ranks, 1 through 50. But imagine if each resolution had a specific network trained for that resolution and dataset. ResNet trained on ImageNet is great, and it's a fine starting point. And it's great to see there is already a difference too. But if we had networks that were a little better suited for our purposes, we can even surpass these lofty expectations. But maybe to unpack some of these numbers and really show you in practice how the pipeline works, here are some examples and differences between the two pipelines. So you take this image of two people on a horse in a field. If you're simply searching for the nearest neighbors using the whole image, it might look for grass, it might look for a clear sky, but it's not discreetly looking for things like the horse or for things like the people, so the matches aren't going to be great. Whereas if you look at multi-resolutional search, it finds all in its top 4 are horses and people on fields. Really, ideally, what we're looking for in our use case. Another interesting aspect when it comes to CNNs is dual counting. This is something that they're not traditionally good at, and as you can see, when we search for this image of 2 giraffes, we do find giraffes, but with a traditional search, we only find 1 giraffe in each image. What do we find with multi-resolutional search? 2 giraffes in each image. Why? Because when our algorithm, when we're tiling and we're aggregating the data, there is, greater incentive to match with 2 giraffes because we tiled it twice. And so to quickly speak to the software engineering aspect of things, another benefit of my pipeline comes from the way in which it was developed. Throughout development, I focused on efficiency, modularity, and documentation. I've exposed the functions that the user needs and withheld the gory details for only me to worry about. And we're working towards making the code a public GitHub repo so that any user can download and use my code and potentially plug in some of these other awesome innovations that we've seen throughout today to make the pipeline even better. We would even want to create test cases that can show the user precisely how to use our code. So in summary, I identified 2 problems that traditional search methods would face in a satellite image search ranking pipeline and developed an alternative strategy. I used industry standard techniques and approaches for development and testing, and I found a marked benefit to my approach. From a software engineering standpoint, I focused on keeping the code efficient so it would scale and readable so it could be easily used. When attacking hard problems like finding a needle in a haystack, our only hope is to make those hard problems a little bit easier. Hopefully, this project can bring someone a little bit closer to finding their needles and becoming their own Hay King. Thank you.